We all know that the abbreviation for laser is light amplification by stimulated emission of radiation. Does this mean a laser is also a form of light? Yes, a laser is also a form of light, but it differs from light in three important properties or characteristics. Let's see what the three important properties of lasers. The three important properties of lasers are collimation, monochromatic, and coherence. What is collimation? Collimation means traveling in one direction. The laser rays always travel in one direction from the source, whereas light rays travel in all directions from the source. What it means is that when you generate or produce a laser, all the laser rays emitted from a source will travel in only one direction. Whereas when a light is produced, all the light rays emitted from the source, bulb, will travel in all directions. Images show light rays from a bulb traveling in all directions. Laser from source travels only in one direction. The second property is monochromatic. Monochromatic means the laser rays are of one color. For example, KTP laser will have a laser beam of green color only, whereas light from a bulb will have multiple colors. The bulbs and tube light that we use in our home also have multiple colors, though they appear to our eye as a single color, white or yellow. This means each laser waves are in phase in space and time, whereas light waves are not in phase. You can see in the diagram that all laser waves are aligned in phase, whereas light waves are not in phase. Wavelength. This is an important specification of a laser. Each laser has a unique wavelength. This wavelength decides or determines the characteristics of that particular laser and its application or treatment. Wavelength is the measure of the length of one full wave. It is usually mentioned in nanometer, nm, or micrometer, μm. You can see in the slide each laser is mentioned with a unique wavelength. Ruby wavelength is 694 nanometer, Alexandrite laser wavelength is 755 nanometer, Nd:YAG laser wavelength is 1064 nanometer. You can also see the wavelength of a few other lasers. Later in this presentation, we will see how this wavelength determines the characteristic, chromophore, of the laser. The electromagnetic spectrum is a pictorial representation of all ranges of electromagnetic radiation or waves. It is the entire, continuous range of all possible frequencies and wavelengths of electromagnetic radiation. It spans from long-wavelength radio waves to short-wavelength gamma rays, including visible light, X-rays, microwave. All electromagnetic waves travel at the speed of light in a vacuum. Laser is also electromagnetic radiation. In the diagram you can see the wavelength of all the electromagnetic radiation, like ultraviolet rays in 10 nanometer to 400 nanometer, visible light from 400 nanometer to 700 nanometer. You have laser at a wavelength of 400 nanometer or 800 nanometer or at any of the above-mentioned wavelength in the electromagnetic spectrum. Figure shows the various laser wavelengths in electromagnetic spectrum. You can see excimer laser wavelength falls in ultraviolet wave range, KTP laser in 532 nanometer, green color. Ruby laser at 694 nanometer, red color. You can see Nd:YAG 1064 nanometer, holmium 2100 nanometer, erbium YAG 2940 nanometer and Co2 laser 10600 nanometer. All these lasers in infrared region, means they are colorless or invisible laser. Now we will see laser tissue effects. What happens when a laser is passed on a tissue? You will see following 4 types of tissue effects on laser application. First one is reflection. The applied laser will be completely reflected by the tissue surface. Second one is scattering. The laser gets deviated from the straight path it traveled and gets dispersed in multiple directions. Third is transmission. The applied laser passes through the tissue. Fourth is absorption. The applied laser is absorbed by the tissue. Chromophore is nothing but the component in the human body that absorbs most of the laser energy that is applied. Each laser has chromophore of its own. Some lasers have primary and secondary chromophore. Example, if you pass a diode laser on the skin, the most of the laser is absorbed by melanin in the skin and then some quantity will be absorbed by blood. So the primary chromophore of diode laser is melanin and secondary chromophore is blood. Here is a list of lasers with its chromophore. KTP laser has a primary chromophore of blood and secondary chromophore of melanin. Pulsed dye laser has a primary chromophore of blood and secondary chromophore of melanin. Alexandrite laser has chromophore of melanin. Nd:YAG laser has primary chromophore of melanin and secondary chromophore of blood. Holmium, erbium and CO2 laser has chromophore of water. When a laser is absorbed by tissue or chromophore, the following 4 types of interactions happens at the tissue or target. First, photothermal. Second, photomechanical. Third, photochemical. Fourth, selective photothermolysis. Photothermal. The laser that is absorbed by the tissue is converted into heat to cause various effects like cutting, coagulation and vaporization. In coagulation, the laser that is absorbed by the tissue causes protein denaturation, used for hemostasis. In vaporization, the laser that is absorbed by the tissue causes vaporization of tissues, used in cutting and ablation. In carbonization, the laser that is absorbed by the tissue causes tissue burning or charring. Example of photothermal effect is surgical lasers. In photomechanical, rapid heating of tissue by a laser pulse can create a shockwave that mechanically disrupts the tissue or target. Example, holmium laser used in kidney stone breaking. In photochemical, direct breakage of chemical tissue bonds or chemical interaction with an applied drug, PDT. Example, pulsed dye laser used for treating esophageal cancer. In selective photothermolysis, the matching of a specific wavelength and pulse to selectively absorbed by the target in the tissue with minimal effect to surrounding. Example, diode laser used for hair removal treatment. A laser is generated through a process called stimulated emission. Let's see the difference between spontaneous and stimulated emission. When you apply energy to an atom, the electron in the lower energy level or orbit absorbs the energy and moves to a higher energy level or orbit. After some time, the electron at the higher energy level will emit a photon and moves back to lower energy level. This is spontaneous emission. In stimulated emission, electron at lower energy level is moved to higher energy level or orbit by a photon or energy that applied to the atom. Again, the applied photon triggers or stimulates the electron at higher energy level to emit a photon and move to lower energy level. This emitted photon is the laser. Elements of typical laser. Picture shows the basic elements in a laser machine. Active medium is the material from which the laser is produced. For example, the KTP laser will have active medium of KTP crystal. There are 2 mirrors, they are high reflector and output coupler. The high reflector is fully reflective mirror and output coupler is a partially reflector mirror. And we have energy source. This energy source can be a flash lamp or arc lamp. The photon or energy from this lamp/energy source will stimulate the electron in the active medium to produce laser energy by stimulated emission. The laser that produced in the active medium would travel to high reflector and gets reflected and travels to output coupler and again reflected. This reflection of laser between 2 mirrors, high reflector and output coupler, will amplify the intensity of the laser. Once the laser intensity reaches a particular level, it gets passed through the output coupler and you get laser output from the machine. Laser types. Based on the type of active medium, lasers can be classified into solid, liquid, gas and diode lasers. Examples of gas lasers are CO2 laser, helium neon laser, and argon laser. Examples for solid-state laser are Endiag laser, ruby laser, alexandrite laser. Example of liquid laser is dye laser. Diode laser is different from other lasers because it doesn't have separate active medium and separate energy source or pumping medium. The basics elements of solid laser is same as what we discussed in slide, basic elements of laser. In the basic elements of a liquid laser, you can see that the energy source, or pumping source, is another laser rather than an arc lamp or flash lamp. Here, another laser is used to generate a laser from an active medium by stimulated emission. The figure shows the basic elements of a CO2 laser. You have a glass tube filled with a large quantity of CO2 gas and a small quantity of other gases such as nitrogen and helium. On application of power to the anode and cathode electrodes, the stimulated emission process is initiated in the gas mixture inside the tube. The laser that is generated by stimulated emission travels between the fully reflective mirror and the partially reflective mirror at the end of the CO2 tube. When the intensity of the laser beam increases above a particular value, it passes through the partially reflective mirror and becomes laser output. The laser that is generated in the machine is delivered to the treatment area using 4 types of delivery devices, and they are: articulated arm, fiber optic cable, scanner, micromanipulator. The figure shows articulated arm delivery of the laser. You can see the machine on top of which a tube with joints is connected. This tube with joints is the articulated arm. The schematic diagram of an articulated arm shows the metal pipe with mirrors inside the pipe. The laser from the machine travels through the pipe and gets reflected by the mirror inside the pipe, and is delivered to the treatment area. Video shows the articulated arm delivery of laser in tattoo removal treatment. End of part 1. Thank you for watching.